Hello everyone and welcome to this hands-on tutorial on Hugging Face Transformers library. Today we are diving into the pipeline API from Hugging Face, the fastest way to use models for text, image and audio tasks with no training required. Here is what we will explore. We are going to explore sentiment analysis, zero-shot classification, text generation, speech recognition, image classification and much more. By the end of this tutorial, you will know how to use pre-trained models in minutes from Hugging Face, apply them across different domains, understand how tokenizers and models work under the hood. So whenever you go to Hugging Face Hub and you choose models, and whenever you choose your task, you will understand once you choose a model and click on use this model, after this tutorial, you are going to understand what this pipeline means and how you can load a model directly. So let's jump in. The pipeline interface covers multiple domains over text pipelines like text generation, text classification, summarization, translation, and zero-shot classification, and image pipelines, which include image classification, object detection, and image to text, audio pipelines like automatic speech recognition, audio classification and text to speech, and multi-modal like image text to text. Okay, so it's one API and many use cases. Let's set up our environment. We will use four main libraries: transformers, datasets, evaluate, and sentence piece. Environment, you need to uncomment this cell and run it. All right, before we touch any code, let's talk about magic behind today's tutorial, the pipeline function from Hugging Face. Think of it as your one-liner shortcut to powerful AI models. You don't have to load models, tokenizers, or worry about pre-processing. Just pick your task, give it some data, and you are off to the races. Here are a few pipelines we will explore: sentiment analysis, zero-shot classification, text generation, fill mask, named entity recognition, question answering, and more. So let's go ahead one by now. As a quick reminder, these are all powered by pre-trained transformers, so you don't need to retrain at all. Let's kick off with a classic NLP task, sentiment analysis. In sentiment analysis, we are trying to figure out whether a piece of text is positive, negative, or sometimes neutral. This includes use cases like movie or product reviews, analyzing tweets or feedback, understanding customer opinions. The Hugging Face do this with a single function call. So if we look here, I imported pipeline from transformers library. Then I defined my pipeline with defining the task sentiment analysis. And I did not define what is the model I'm going to use. So Hugging Face will use the default model, which is distill paired base uncased fine-tuned SST2 English. Otherwise, we can define our own model. Okay, let's see it in action. Okay, so if I imported pipeline from transformers and I defined pipeline sentiment analysis as my sentiment pipeline, and I did not specify the model, Hugging Face will choose the default model, which is distill paired base uncased fine-tuned SST2 English. So if I pass this review for one of the products that I have bought, I absolutely love this product, it exceeded my expectations, to the sentiment pipeline, it will return the label positive and with a score 0.99. So this is amazing because you did not need to download any model manually and you got a full prediction with just one line of text. We will see later how we can specify the model of our own choice. But let's now go analyze multiple reviews at once. If we see here, we are calling the same sentiment analysis pipeline, okay? But we are passing 3 reviews from our customers. The first one is clearly positive. The second one is clearly negative. This was a complete disappointment. And the third one was more neutral or mixed. When I run this cell, it will return a label and the score for each one of them. This is a great example of batch inference. You can send a list of apples and get a list of apples. This makes it super efficient for real-world pipelines. when you want to analyze bulk data like customer reviews, survey responses, or social media. Here is where things get more exciting. Zero-shot classification with Hugging Face. This lets you classify a text into labels you define. So the labels are not defined like the example that we have seen, positive, negative, or neutral. Even if the model was not trained on your labels, it will get you the labels that you want. For example, you can take a sentence and say, is this about billing? Is it a technical issue or a customer support? And the model will tell you which fits best. It uses natural language inference under the hood. Models like Roberta or BART decide how well a label entails the input. So for example, I'm using pipeline and I define the task to be zero-shot classification, and the default model would be Facebook BART large MNLI. And I call this my text classifier. And I pass to the text classifier a review that came from one of our customers by email. I contacted support 3 times about my account being locked, but no one got back to me. This is really frustrating. And I passed an argument called candidate labels, and I specified these labels from my side, like billing issues, technical problem, or customer support. Now, once I run this pipeline, the result will be the label and score for each one of these labels. So from the result that I have seen, this is a customer support problem, and I should forward this email or this complaint to the customer support department. This is powerful because we don't need to train a custom model. We can change the label dynamically, and it works on unseen domain. So let's try another example on different domains. So if we run a text classifier on education domain, so this is a review for one of the online courses from one of the trainees that has graduated. And from this review, I want the text classifier to classify it into one of these labels. Is it regarding the course content, instructor feedback, platform usability, and technical issue? And I pass them as a list to the argument candidate labels and run the text classifier. And the pipeline will return to me the list of these labels and their scores. So we do understand now, according to the highest score, that this is a course content one. So here we're using the same text classifier on finance domain. So I have a review from one of our bank clients, and I said, what's the candidate label for this review text? Is it fraud? Is it billing error, customer support, or loan inquiry? The pipeline will return to me these labels and their scores. From the highest score, this is a billing error. So why this is helpful? In industries like banking, insurance, or fintech, customer concerns come in many forms. With zero-shot, you can auto-label them without needing to build a custom classifier. The model will understand the context and predicts something like billing error with some confidence score. Now let's shift to something generative, like text generation. This is one of the core models like GPT-2, GPT-New, or Falcon. You give the model a prompt and it generates what comes next, like continuing a sentence, writing a story, or answering a question. It's useful for writing assistance, poetry and story generation, educational chatbots, and even coding. Let's try it with the default GPT-2 from Hugging Face Transformers. I called the pipeline text generation here, and the model will continue the sentence that I give it as the input. So the sentence is, this tutorial will teach you how to use Hugging Face Transformers libraries to, and the model will continue this generation. You can tweak different arguments or parameters with the call to pipeline, like maximum length, how long the output should be, the temperature, how creative the model gets, and the top K to control the randomness. Okay, and once we call the API, we can see here the generated text that starts with my prompt, and it started generating according to the default arguments settings. If you want faster output, try a smaller model like this. So when you run these cells, it takes time to load the models for the first time and their tokenizers in the memory. But if you rerun them again, it will take shorter time. As you can see in the generate text attribute in the output, the model continues the sentence, maybe by adding some extra text from its own according to its understanding. Now, you can tweak this by defining the maximum length attributes, like how long the output is, the temperature, how creative the model gets, and the top K that defines how to control the randomness. But if you want faster output, try to use smaller model like Distal GB2. Now, to do that, we define that we want to override the default model and use Distal GB2 from Hugging Face Transformer. It's a lighter version. It's a typo here. It is a lighter version of GPT-2 for faster generation. So I defined now return two sequences with maximum length of 50. So we can compare which output, and we can notice that it is faster than the regular default model. Okay. Now let's try a larger model. Let's introduce you to the Falcon 7P instruct model. This is an instruction-tuned version of Falcon optimized to follow human prompts better than the standard GPT-2. It's perfect for educational tutors, chat-style responses, and task-based prompting. Now, as a head-up, this model is really large. You will need a GPU with lots of memory if your CPU does not have one. If you are using Colab or low-resource setup, you might hit the CODA out-of-memory error. Still, this is a great demo of what is possible with the state-of-art transformers. So I defined the pipeline API with text generation, and that chose my model to be Falcon 7P instruct from TII-UAE. So let's call this text generator, and I give the same prompt with maximum length equal 50. Okay, so if we are running on a regular CPU with large memory, it will take a little bit time to load the model, and let's see the output. As you can see, it finished loading the model and its tokenizer, which takes a little bit of time according to your environment. And now it's generating the completion prompt. So it takes a little bit of time. You can also watch how consumption of your resources is being done. So it uses like 33 gigabytes of RAM. And now it finished generation. So if we look at the generate text, this tutorial will teach you how to use the Hugging Face Transformers library to perform word embeddings on text data. And we can see that the generated text is more real than the previous models. Next up is FIL-MASK, also known as masked language model. This is how models like BERT are trained. Learn to guess missing words in sentences like the following. Transformers are a powerful tool for solving, then there is a masked word that I want the model to predict it. So I define my pipeline with the task FIL-MASK, and then I pass my sentence with the tokens that I wanted to predict it inside a mask HTML tags or square brackets that depends on the model. The FIL-MASK pipeline gives us the top likely replacements for the mask token along with the confidence score. This is useful for language modeling, sentence completion, grammar experiments, and domain-specific understanding. Well, it loads the model and its tokenizer, and then it will generate that this masked word could be the word complex with this score, followed by the word every day with this score. So it can be transformers are a powerful tool for solving complex tasks, or transformers are a powerful tool for solving everyday tasks, and you choose the best that fits your. Let's pause here. This model can return predictions like NLP or classification depending on the training it has seen. We can change the top K to see more options and use different models like Roberta Base. So let's try the FIL-MASK pipeline in different domains. So, for example, I can use a finance example. The company's quarterly mask exceeded market expectation. And another example from the education domain, students are encouraged to submit their assignments before the, and then there is a masked word. Mask And in the legal domain, according to the new law, all businesses must, and they want it to predict this masked word with the updated regulation. For every example in these domains, it will return a list of predictions for each one of them and their scores. For example, for the finance domain, the word earnings with 0.468, and this is the sequence with this completion. So exceeded with the masked word replaced by the token or the word that it predicted, followed by the less scored like results. So if we can see here, we have a list for every example. Let's run it. Here is why that matters. That kind of masked predictions lets you test how well a model understands the domain-specific language on hand without having to train one from scratch. For example, in finance, it might predict earnings or reports. In education, it could be deadline or due date. In legal, it could be comply or register. This is great for exploring model generalization across industries and compare models to choose the best one that fits your task at hand. Now let's move on to the named entity recognition, or NER. NER pipeline helps identify important keywords in a sentence, like the names of people, places, or organizations. To execute it, let's import pipeline from transformers. Then we define NER with grouped entities equal to, and then we pass our article or news or review or whatever to this NER pipeline and run it. It loaded the model and its tokenizer, and then it returns entities like Joshua Pinchu as a person, then Mila as an organization, and then Montreal as a location. NER is great for news tagging, searching, indexing, and resume parsing. Also, it's even good for legal documents. Next, let's look at the question answering, one of the most practical NLP tasks. Okay, question answering pipeline extracts an answer span from a given text. The pipeline will search a context with the most relevant span that answers the questions and return the answer and confidence score. So as you expected, we will define our pipeline with question answering, and we will call it QA. Then we will pass to this pipeline two things: my questions, like who gave a keynote in Montreal, and the context, which could be the text, paragraph, or even book. And this is the basis of RAGs, retrieval augmented generation. So if we run this cell and we do not specify a model, Hugging Face will choose the default model to be distal paired base distilled square. So the model returns Joshua Pinju, and it tells me that this answer exists from position 0 until position 13, and this is the answer. This is called extractive question answering, and it is incredibly useful for chatbots, search tools, interactive learning. Now let's move to text summarization, which is the art of turning long text into something shorter while preserve the meaning. There are two types of text summarization: extractive, which pulls out key sentences, and abstractive, that rewrites the contents in new words, more like a human would do. This is great for summarizing news and research, creating meetings notes, and digesting emails or reports. Let's try it in the following cell. Similar to previous tasks, I'm going to define my pipeline to be a summarization task, and I'm calling it a text summarizer, and then pass a text of articles from the news, and I wanted to summarize it. If I did not specify the model, the default model from Hugging Face is distal paired CNN 12.6. Now, if we run it, it will load the model and its tokenizer. And the model will read the long article and generate a shorter paragraph or version from it, capturing main ideas in essence, just in seconds. This is perfect for staying informed without reading everything line by line. And you can see it, and we can see the output inside this summary text, and it is much shorter. Next up is machine translation. Machine translation converts text from one language to another. Hugging Face supports hundreds of languages through the models like Marianne Machine Translation, Impart, MT5. It's good for use cases like globalized applications, chatbots, or learned resources in multiple languages. To use machine translation from Hugging Face, we call the pipeline with the translation, and we define our model according to the language that we want. In this example, we are going to translate from English to French, and we call this text translator. We pass our input or prompt in French, and we expect it to translate it in English. So it started by Mila, and it is l'Institut québécois d'intelligence artificielle est reconnu mondialement pour until the end. And once we run it, it loads the model and its tokenizer, and then it gives us the output. Mila, the Institut québécois d'intelligence artificielle, is recognized worldwide for its or her cutting-edge research and so on in English. So this is how it translates the sentence naturally, keeping the meaning and the tone intact. You can flip the direction of the models from French to English, to Deutsch to English. Now let's pivot to vision model and move on to the image classification. Image classification helps model to recognize objects, people, animals, and textures. Hugging Face supports models like vision transformers. So I'm loading an image from the famous Coco dataset, and I'm previewing the image to you, and we can see that it is an image for two kitties. Okay. So I'm loading the pipeline with the task is image classification, and by default, it will use the default model Google Vision Transformer base batch 16-224 as an image classifier, and I pass the image URL, and I will receive the output classes or labels inside my image class labels variable, and I will loop over the labels that I received and print the class labels and their scores. So it will load the model first, and the transformer pipeline will give me that the first one is Egyptian cat with the score 0.93. The following is tabby cat with less score, and so on. So we can expect that this model might return labels like zebra, sports ball. That all depends on what it sees. It uses vision transformers under the hood with no fine tuning needed. It's good for applications like content moderation, product tagging, or smart photo albums. Now let's shift to audio. Automatic speech recognition, or ASR, converts spoken audio into text, which is the backbone of tools like voice assistants, auto captioning tools, audio note transcriptions. We will use a shortwave file from the Open Speech repository. Let's upload the file. You can download it from this link, and let's run it for you, and let's listen to it. So we will use this shortwave file from the Open Speech repository and pass it to our transformer audio model and transcribe it into its English language. So to do so, let's call the pipeline with the task is automatic speech recognition, and we define the model from OpenAI Whisper Large version 3. And if I did not specify the model, it will use the default one, which is the Facebook Wave2Vec 2 based 96 Hz. So I'm calling the ASR pipeline, the automatic speech recognition pipeline, and I will return and I will pass to it the audio file with the chunk length, and we can define parameters like return timestamp or what's the stride length, and I will receive the transcript, and I wanted to print the transcript text for this audio file. Now it loaded the model and its tokenizer, and at the end it gives me the text that exists in this audio file. Note that Whisper model handles many accents, languages, and even background noise. This kind of technology powers meeting transcript, podcast indexing, real-time captioning. Now try your own .wav file or whatever audio file to test how well it works on different. So far, we learned how to use Hugging Face pipeline APIs for sentiment analysis, zero-shot classification, text generation, fill mask predictions, named entity recognition, question answering, translating, summarization, image classification, and even audio transcription. One API, multiple modalities, no fine-tuning, just powerful pre-trained models. So before we continue, Now you can go to Hugging Face Hub and choose the models, and based on your task you can choose models, and you can choose the model, and you now understand how to use this model using Transformers pipeline. Okay, now before we continue, if you found this tutorial helpful, please don't forget to like the video and drop any questions in the comment. Subscribe for more AI and ML content. We have been using the pipeline function like magic, but let's demystify it. Under the hood, pipeline combines 3 core components. Let's walk through these steps manually so we understand how pipeline API or function works. Before models can do anything, your text must be pre-processed, so they enter the tokenizer. The tokenizer breaks down your input, maps tokens into IDs, and adds a structure. Think of it like converting a sentence into language that the model understands. So it splits your raw text into smaller units. We call them tokens. So if your text transformers are awesome, then they will be transform are awesome. Okay, so you can notice that some words can be more than one token. Then they map them into IDs according to the vocabulary that the model was trained on. So each token will take a number from the vocabulary ID. Then it adds some special tokens like CLS or separator, or start of sequence or end of sequence, depending on the model architecture. We will explain this later, don't worry about that. The tokenizer returns a dictionary with input IDs, which are the tokenized integer ID to the text, and the attention mask, which is either 1 or 0, 1 for real tokens and zeros for padding tokens, as we shall see. So the tokenizer will be a list of IDs according to the token IDs, and at the beginning you will find some special token IDs. We will talk about that later, so don't worry about that, and an attention mask that tells me that these tokens are part of the input sequence. So let's recall and bring back the sentiment analysis for the context. This is what we are about to replicate manually. Okay, so remember that we used the pipeline with sentiment analysis, and we passed 3 reviews, and it returns to us the labels for each review text and the score for this label. So the first review was positive, then negative, and the last review was positive as well, with a less score than the first one. So let's walk through these steps and better understand what's happening under the pipeline. Let's start with step 1, which is pre-processing with tokenizer. We will start by loading the tokenizer manually and encoding our reviews. This gives us input IDs and attention masks, what the model actually uses to generate its output. So from transformer, I will use the auto tokenizer class, which will be used to split the text into tokens and convert the tokens into integer IDs using a vocabulary, and adds the special tokens for the task for this model, which is classification and separator. So this is the checkpoint for the model that I'm going to use, and I'm loading the auto tokenizer class from this checkpoint. And this is the list for the reviews that I'm going to pass to the tokenizer. So I'm calling the tokenizer, I'm passing the reviews with padding equal true. We are going to understand what does this does as well, and truncation equal true, and return PyTorch tensors into reviews inputs. And let's print the reviews inputs that came out from the tokenizer. As we can see, it loads the tokenizer, and for each review text, it has been tokenized, and these tokens were replaced by their token IDs. So this is the first review, the second review, and the third review. And I will find that in the first review, I have some tokens with 0. This is what we mean with padding. While the second one was long, there were no added or padded tokens. And the third one was shorter, so it has some extra padded tokens. So it generated also an attention mask that gives me 1 for real tokens, and for all added or padded tokens to the short sequences, it puts an attention value of 0, which means it tells the model don't give attention to this added or padded token. So if I print only the input IDs, it will give me the list of token IDs for each review. Now that we have tokenized our input, it's time to send it into a model. So we will load a pre-trained model using the auto model class. Auto model class gives us access to the core transformer engine, but not the classification layer. But take care. Always load the tokenizer and model from the same checkpoint. Otherwise, your tokens might not be aligned with what the model expects, which leads to wrong or invalid predictions. So we will import auto model from transformers. We will use auto model from the same checkpoint that we used for the tokenizer. We will pass the reviews inputs, which were the output of the tokenizer, okay, to the model. And we will pass it to the model and we will get the model output. Let's print now the model output shape and we will see that it is a 3 by 31 by 768. So it loads the model and it returns to me 3 sentences or 3 sequences. Each one sequence is 31 tokens length and each one of them is 768 numbers or embeddings. And this is what we call it the last hidden state from the model. So what we have done here is that we loaded the raw model, we processed the input, and the model gives us the embeddings and not the predictions. This is useful for tasks like sentence similarity or custom classification heads. Hugging Face gives us really different variants for different tasks. Like auto model, as we have seen, it returns for us the last hidden state, which gives us the real raw embeddings, or auto model for sequence classification, or causal model, or masked language model, multiple choices, and so on. Each one of these gives as a classification head or a question answering logic to the end of the transformer model. So always match the model type to your task, depending on your problem on hand. So all these variants wrap auto model with a task specific head, so you don't need to build one manually. So we will learn more in our next tutorial, not how we can add a classification head, and we compare it with fine-tuning a pre-trained model as well. So let's load task-specific model. For sentiment classification, we want predictions and not embeddings. So we are going to use auto model for sequence classification class, which comes in. It has a built-in head for classifying sequences. So we load this class from transformers, auto model sequence classifications, and we load it from the pre-trained at this checkpoint, and we call it a model. We pass now our review inputs to this model, and we get the model outputs. Now, when we print the model outputs, we print the logits.shape, which gives me the 3 by 2 matrix or PyTorch tensor. So it means that we have 3 sentences, and for each label, either positive or negative, it will give me a score. Okay, so if we print this has 3 sentences with 2 labels, and this is the score. So the model is now returning the logits or the raw scores for each class. So for 3 reviews and 2 labels, the shape will be 3 by 2, and these are the logits. Now let's apply the softmax function to these logits, and let's get the predictions. Logits are not probabilities yet. We apply softmax to normalize the value so they add up to 1 across the classes. So if we see for the first review, this adds up to 1. And the index for the first label is 0, and the index for the second label is 1. Now, if we want to translate these probabilities into actual labels like positive or negative, let's see how we can do that. So let's print the ID to labels dictionary from the model configuration. It tells me that 0 index is negative and 1 index is positive. Now I want to transfer these logits back into results as labels. So we will use torch argument max over these predictions, and we will get the predicted label indices. And for each one of them, I will print the label, and it will give me that the first one, the highest score was positive, as we can see here. Okay, and the second review, it is negative, and the last one is positive. This has been done that it will go through all index in the predict label indices, and it will get the ID to labels index for the items after we get the argument max or the index of the highest value in each row. And now we translated those probability scores into actual predicting labels which are human readable. If you have noticed, you have just manually rebuilt what the pipeline does behind the scenes. If you don't know how you can create transformer model from scratch, let's use the BERT_config class. While most use cases rely on pre-trained models, it's also possible that you can manually configure and initialize a transformer from scratch. It means that it starts from random weights. If we use the BERT_config and the BERT model, and we import them from the transformers library, we can define the BERT configuration and then print this BERT configuration for the famous BERT model. And we can see that what's the hidden state size, we can see the number of hidden layers, other configurations for BERT model, and then initialize a model with random weights using the BERT model class and passing the BERT configuration model. However, so model now is exactly the same as BERT model, but with random weights. So this is only for experimentation and learning. It won't give meaningful predictions out of the box. And if you want it to do so, then you need a lot of time and tons of data to train it. Which means that this model is just like a blank template. So it's freshly built with random weights. So why this is important, it shows us how transformers are structured under the hood. You can experiment with custom model shapes, layers, and hits, etc. But training from scratch takes really tons of data and compute. So that's why we almost always use from pre-trained function to start with a solid base and pre-trained model, and we fine-tune it on the task on hand or with the data that we have on hand. So that's why we load a model that is already trained, which is more simpler and gets meaningful output. So from here, I can import the BERT model. I can load BERT model from a certain training or checkpoint model, and I can save it locally inside my folder using the model.save pre-trained inside a BERT folder that I'm going to give it a name BERT model. So if I run this cell, it will load the model and it will create a folder named BERT model. We can see it here, okay? And then if I list what are the files inside this model, I can find the configuration.json and the model tensors. So if I open the folder, I can see here the configuration.json. If I open it on the right, we can find all the configuration for these models. This saves the model so we can use it offline, in production, or even during. Instead of using the BERT model class, we can use the auto model class because it's a checkpoint agnostic, which means that it can load any model that shares the same architecture like Ruperta or distal pair. This gives us really flexibility when swapping models for experimentation or benchmarking. So we can use auto model. So we can import auto model from transformers. Then we can define our model from pre-trained checkpoint, and it's the same. So let's go back to tokenization and auto tokenizers. As we first step of NLP pipelines, with auto tokenizers, we can convert text into tokens, and we can convert tokens into IDs and decode IDs back to text. So let's import the BERT tokenizers from the transformers from this checkpoint BERT base case, and then we can pass a text to this tokenizer, and let's see what is the output of the tokenizer. So if we print tokens, it will give me the list of input IDs, which has all the token IDs and the token type depending on the model, and the attention mask for this text. Okay. So the output of the tokenizer will be a dictionary that has all the encoded values like the input IDs, token type IDs, and the attention mask. Great. So as you can see, it loaded the tokenizer configuration and the list of all the vocabularies in this tokenizer. Okay. So similar to BERT model and auto model, instead of using BERT tokenizer, we can use auto tokenizer class. it automatically loads the right tokenizer based on the model checkpoint, which makes your code more reusable. So again, from transformers, we can import the auto tokenizer. From pre-trained, model checkpoint, and we call this the tokenizer, and we give it the same input text, and we get the tokens, and we can now convert these tokens as IDs to convert tokens to IDs. We will get the token IDs, and we will print both the tokens and the token IDs. Similar to BERT model and auto model classes, we use auto tokenizer instead of BERT tokenizer. So it automatically loads the right tokenizer based on the model checkpoint, which makes your code more reusable. So we'll import the auto model from the transformers. We will load it from the same pre-trained model checkpoint and pass the same text and print the tokens, and we will get the same output as above. These tokens IDs are what exactly goes into the model as input and not the raw text. Now let's see how we can save our tokenizer into disk to load it later. This is also useful for production or deployment. And let's examine also the tokenizer in depth. So we can run tokenizer.save pretrained, and we will save it inside a folder called myBERT tokenizer. So when I run it and I refresh on the left, I can see here that I have the special tokens configuration, the special tokens map, the JSON, the tokenizer configuration, the JSON, the vocabulary text, and the added tokens, and the tokenizer.json. So this writes multiple files, including the vocabulary and the configuration JSON files, into my folder called myBERT. So if we open the vocabulary.txt, we'll find all the special tokens and the regular tokens that is used by the tokenizer. This list has been built during training. So let's examine the tokenizer by passing an explicit review. So the review was, it works as intended, though there is nothing particularly special about it. So this is my text, and I pass it to the tokenizer, and I'm calling the function tokenize, and it will return me this text but split into tokens, including even punctuations. It will give me a list of all tokens. Now, if I pass these text tokens to the function that says convert tokens to IDs from the tokenizer, it will print me the list of tokens. Okay, now let's decode this list of tokens back into text. We can call the function called decode, passing these text token IDs and store the result into the text decoded. Or we can just call the decode and pass the list as a copy and paste as the argument. And let's print the text decoded, and it will give me the original text back. Transformers often break words into subwords to handle unknown vocabulary. So it's possible that you can find some words that has been split into sub-tokens. So the decode function does what we call it a reverse mapping, which is super helpful for debugging or understanding what your model is saying internally. Now let's move on to the special tokens. Transformer models rely on few special tokens to understand the structure of the input. This could include CLS, like the start of the input, and this is usually used in classification tasks. We have also SEP, which separates segments, used in question answering and natural language inference, and BAD for batting, and mask, that is used for masked language model like BERT. These tokens are automatically added by auto tokenizer. So now if we pass the text to the tokenizer and we print the input IDs, we will find that this list is exactly the same list that we have here. But what is different is that the tokenizer has added special tokens, one at the beginning and one at the end. The token ID 101 and the token ID 102 corresponds respectively to the CLS and the SA tokens. So these tokens are signal to the model where the input begins, ends, or even. So if we see in the following list, we are printing the special tokens map for the tokenizer and the special token maps values, and we convert the tokenizer special token maps into values and print all this. We can see now that these are the tokens. UNK for unknown token, SAP for separator token, BAD for bad tokens, and so on. And these are the dictionary values, and these are the token IDs in the vocabulary, the text. So if we open the vocabulary, the text, and we move on to tokens starting from 101 and 102, we can see that these are the special tokens that we described earlier. So let's tokenize another review. So we have a review that is the product is fine, but the delivery was delayed. We pass it to the tokenizer and let's print it. And we can see that the tokenizer returned a dictionary with the input IDs and the token type IDs and the attention mask. And notice that it added also special tokens, 101 and 102. Now let's bring everything together. We will tokenize input. We will prepare it as tensors. We will send it to a sequence classification model and decode the results. We will also use the attention mask, which ensures that the model does not pay attention to any batting tokens. This is how real-world classification pipelines are built manually. Okay. So in the following code, we imported torch, we imported auto tokenizer, auto model for sequence classification. So this is a transformer model with a classification head added to it. We specified our checkpoint, and then we load the tokenizer for this checkpoint. So we said tokenizer equals auto tokenizer from pre-trained this check model. And then we also loaded a transformer model for sequence classification from the same checkpoint. This is our text. Okay. Then we pass the text through the tokenizer and tokenize it into text tokens. We convert these tokens into IDs and we get the output named text token IDs. We pass these text token IDs and convert it into torch tensors. So I call it text input IDs, and we print it. And then we pass it to the model that will generate the model outputs. And then we print the logits from the model outputs. Let's see what happens now. So if we run it, it printed the input IDs from the tokenizer as a torch tensor, and this is the logits from our model. So you can pass these logits to the softmax function and then get the argument max to get the maximum ID for each label and get the label for the prediction. Now let's pause here to explain what attention masks are and why they matter. Transformer models cannot handle variable input lengths directly. So we batch shorter sequences or we truncate the longer ones. So attention masks tells the model which tokens to consider by assigning a value of 1 to the real tokens and which tokens to ignore by assigning 0 to it. So it means that this token is batted. To see the bad token ID, we call the tokenizer the bad token ID to know which ID the tokenizer gives for a bad token. So when we pass the argument batting equal true to a tokenizer, the tokenizer will get this token added at the end of the short inputs. We will use this in the next cells to explore how batting works with attention masks. So if we look here at these review IDs for some text, okay, and these ones, we will find that in the first cell, we have 2 reviews of the same length. However, in this list, we have 3 reviews. The first one is length of 6 tokens. The second one is 5 tokens, and we add a bad token. And the third one has 3 tokens and 3 bad tokens. So for each bad token, the attention mask should include zeros entries. So if I pass the reviews IDs and the attention mask to the model, converting them into torch tensors, okay, and gets the model output, I can see the logits for this model. I can see the logits output from this model. Now, let me change this some zeros to P1s. It means that I'm telling manually the model to give attention to all 3 tokens in the last review. Now, look exactly what happens here. If I run this, the results has changed. Okay, so let's put it back and run the cell again, and we will get the initial values. Okay, this cell simulates how we mask out batted tokens, so the model does not learn from meaningless inputs. Let's replace this example with a real example. So if I have a list of reviews, the first review is this movie was amazing, and the second one was terrible acting and awful plot. And we call the tokenizer, passing these reviews with padding equal true and return tensors. And let's print the attention mask. We can see that the first review has one extra token that has been padded to it to match the same length as the second one. If I add more sentences here, text here like I don't recommend it, okay, and run again, we will find that the first review has more padded tokens. So what happens is that Hugging Face will automatically pad shorter sequences and generate the attention masks, which saves you the pain of manual setup. Note in mind that transformers have maximum sequence length, and usually it's 512 or 1024 tokens, depending on the model. If you exceed this, the models might crash or the tokenizer will truncate the longer sequences. You can solve this by using models with extended maximum length and truncate your inputs. Okay, now in this, if I replace this review with reviews and I run the same cell again, instead, it will give me the input IDs and the attention masks for all the list of 3 reviews. Transformer tokenizers come with several padding strategies. We have 3 main padding options in Hugging Face. The first one is padding with the longest, which means it pads the sequences to the longest sequence in the batch, or maximum length, which pads the model, to the model maximum length, and the padding equal maximum length with maximum length equal n to fixed custom length. You can also truncate long sequences using truncation equal true. This cell shows all these 3 main padding strategies. In the first part, we have the same reviews with padding to the longest. And we print the reviews token input IDs and their attention mask to compare it with maximum length and the padding with maximum length and maximum length equal 8. And you can see now in the output the difference between each padding strategy. To summarize which padding strategy to use, padding with longest is good for training, padding with maximum length is best for exporting or on-device inference, and using truncation equal true with maximum length is useful for strict length control. All these strategies helps you avoid crashes, improve memory use, and build robust pipelines. And remember that in best practices, when we have like a long review, as humans, we can understand or we can define or classify the sentiment from the first 2 sentences or 10s or 20s tokens, and we don't need the remaining reviews. So in best practices, what's usually being done is that we can truncate long sequences, and we can also add the review title to the review body if it exists. Tokenizers can also return tensors in the format that matches your machine learning stack. So you can use return tensors as PyTorch or TensorFlow or even NumPy. All this can be done by specifying this argument when you call the tokenizer. And you can see the output here. So Hugging Face makes it really easy to block one line. You can adapt your tokenizer output to your preferred deep learning framework. So let's have now a full round trip how the tokenizer take the text into tokens and then tokens into IDs and back to text. This is good for sanity check to a pipeline is working properly and you understand everything. So first I print the original review. So this is the original review text and this is the review text that we have seen before. I absolutely love this product. Then I call the tokenizer, passing this review to the tokenizer and print the review tokenized. And from the review tokenized, I will print the input IDs and the attention masked, and then I will use some separator to decorate the output. If I run this, this is our original review, followed by the input IDs, followed by the token input IDs, and we can see that it added the special tokens to the beginning and end, and to the end, and then we have the attention mask. Now let's print the review tokens. So call the tokens functions from the review and store it into the review tokens and print them. And we can see now the review tokens to start with the CLS special token and ends with the separator. And then for each token, I will have it even for the punctuation. Now, after that, I will convert these tokens into IDs, okay? And we print it. Followed by that, I will print with the special tokens, and then I will encode it without the special tokens. So I will pass add special tokens equal false. So we can see now that these are the token IDs without the special tokens 101 and 102 at the beginning and at the end. Then I will decorate the output again, and then I will decode the review token IDs back into text. So I will call the decode function, one with the special tokens and one without the special tokens. So when I pass the IDs, these are the tokens decoded back into understandable format to the humans. And this is the original text without the special tokens when I pass skip special tokens equal true. So this is good for sanity check. So you understand how we can go forward and backwards with our tokenizer. Now, before we finish, let's do one last full review classification pipeline. So we'll tokenize the batch. So we will tokenize a batch of inputs. We will feed them into a model, and we will use the softmax and argmax to get the predictions, and we map the claim into a human readable label. And in that way, we will understand what is happening under the pipeline API. So this is a full custom classifier that mirrors what pipeline function does. Now you will have a full control by importing the torch. Then we get our auto tokenizer and auto model for sequence classification. We define our checkpoint, and then we load the tokenizer for this checkpoint and the auto model for sequence classification from the same checkpoint. So they are pre-trained model and pre-trained tokenizer for the same model. And I have a list of short reviews, so manually, okay? So we have 3 reviews. Then the first thing, I will take these short reviews and pass it to the tokenizer with padding equal true, truncation equal true, and return a PyTorch tensor. And I will receive the output into a short reviews tokens. I will pass these short review tokens dictionary that has the input IDs and the attention mask to the model, and I will get the model outputs. Outputs will contain the logits of the transformer model, and I will print it when we will see it right away. And then I will apply the softmax to these logits, and I will use the argmaximum to get the label index, and decode it back using the iteration ID to label, and I will get the prediction labels, and then I will predict the labels. So if I run this cell, okay, you can see that for my 3 short reviews, these are the logits, and then they went through a softmax, and then we mapped the index for the labels, and we get that the first one is positive. Yes, it's correct. I absolutely love this product. The second review is negative. This was a complete disappointment. I will never order from this company again. And the last one is positive. It works as intended. Okay. And congratulations, you have just completed a full hands-on walkthrough of the Hugging Face Transformers pipeline from high-level pipeline function API to the low-level internals. So let's recap what we have learned so far. So we have learned what pipeline function does and how it simplifies common AI tasks. We learned how to run sentiment analysis, zero-shot classification, text generation, NER, question answering, summarization, and even image and audio models. We learned how tokenizations, embedding, and attention masks, truncation, and special tokens work. We learned how to decode model outputs manually using the softmax function and the argument maximum. And we learned what's the difference between the auto model and the auto model with task, or dedicated for tasks like auto model for sequence. So what's next? Next is you can try fine-tuning a model using the trainer API. We will have a dedicated tutorial to that, and trust me, it will be less shorter, so it's not going to be that long. You can also explore other pipelines like translations and question answerings. You can combine transformers with LangChains or Gradio for full stack apps, accelerate and datasets to build scalable training pipelines. If you enjoyed this tutorial, like the video, subscribe to my channel, and start the repo on GitHub.